The Big Bang is how astronomers explain the way the universe began. It is the idea that 13.8 billion years ago the universe began as a single point just a few millimeters across, then expanded and stretched to grow as large as it is right now and still stretching. Today the Big Bang model is a broadly accepted theory for the origin and evolution of our universe. However, in 1920s, the scientific community believed that the universe is static and the universe was neither expanding nor contracting, that is, overall space between galaxies did not change. Even Einstein believed the same. So in 1915, when his general relativity theory predicted an unstable universe that would either expand or contract, he deliberately invented a cosmological constant as a term in his general relativity theory that allowed for a static universe. In 1927, Lemaitre, a young Belgian scientist, proposed that the universe is expanding, deriving the notion mathematically from Einstein's theory of relativity. When Einstein and Lemaitre met that same year, Einstein told him, "Your calculations are correct, but your physics is atrocious." Einstein did not question the math, but he could not accept the finding. When Edwin Hubble discovered astronomical evidence of expansion 2 years later, Lemaitre's theory was confirmed. Edwin Hubble announced that his observations of galaxies outside our own Milky Way showed that they were systematically moving away from us with a speed that was proportional to their distance from us. The more distant the galaxy, the faster it was moving away from us. The universe was expanding after all, just as general relativity originally predicted. The popular belief is that after Einstein met with astronomer Edwin Hubble at California's Mount Wilson Observatory in January of 1931, Einstein was so impressed by Hubble's evidence of an expanding universe, he renounced his belief in a static universe. Hubble showed Einstein photographic plates of distant galaxies, which showed that the farther away it was from Earth, the redder it was, a phenomenon called redshift. As a distant galaxy recedes away, its light waves get stretched out and white light takes on a reddish hue. The farther away, the faster it recedes and the redder the galaxy looks. As a result, when it became clear that the universe wasn't actually static but was expanding instead, Einstein abandoned the cosmological constant, calling it the biggest blunder of his life. At the same time, a more existential question was born. If the universe is expanding, does that mean it originated from a specific point in time and space? In 1931, in a now legendary paper published to the journal Nature, Lemaitre answered yes. The universe began as a primeval atom, he argued. Today this idea is better known as the Big Bang. According to the theory, Big Bang did not occur at a single point in space as an explosion and expand into space, as space did not exist before the universe. It is better thought of as the simultaneous appearance of space everywhere in the universe. Universe is only as vast as it is today due to the fabric of expanding space. Space itself has been stretching and carrying matter like stars, galaxies with it. When the universe was just 10 to the power minus 34th of a second or so old, it experienced an incredible burst of expansion known as inflation, in which space itself expanded faster than the speed of light. Inflation was both rapid and strong. It increased the linear size of the universe by a factor of 10 to the power 26 in only a small fraction of a second. According to NASA, after inflation the growth of the universe continued, but at a slower rate. As space expanded, the universe cooled and matter formed. 1 second after the Big Bang, the universe was filled with neutrons, protons, electrons, anti-electrons, photons and neutrinos. During the first 3 minutes of the universe, the light elements were born during a process known as Big Bang nucleosynthesis. For the first 380,000 years or so, the universe was essentially too hot for light to shine. The heat of creation smashed atoms together with enough force to break them up into a dense plasma, an opaque soup of protons, neutrons and electrons that scattered light like fog. This early soup would have been impossible to look at because light could not carry inside of it. The free electrons would have caused light, photons, to scatter the way sunlight scatters from the water droplets in clouds. However, the universe was expanding, and as it expanded, it cooled, as the fixed amount of energy within it was able to spread out over larger volumes. After about 380,000 years, it had cooled to around 3000 Kelvin, and at this point, electrons were able to combine with protons to form hydrogen atoms, and the temperature was too low to separate them again. In the absence of free electrons, the photons were able to move unhindered through the universe. And universe became transparent for light. The Big Bang theory predicts that the early universe was a very hot place and that as it expands, the gas within it cools. Thus the universe should be filled with radiation that is literally the remnant heat left over from the Big Bang, called the cosmic microwave background. You can't see the cosmic microwave background with your naked eye, but it is everywhere in the universe. It is invisible to humans because it is so cold, just 2.725 degrees above absolute zero. This means its radiation is most visible in the microwave part of the electromagnetic spectrum. It was first predicted by Ralph Alpher and other scientists in 1948 while studying Big Bang nucleosynthesis. It was found only by accident almost 20 years later. Scientists Arno Penzias and Robert Wilson, both of Bell Telephone Laboratories in New Jersey, America, were building a radio receiver in 1965 and picking up higher than expected temperatures in every direction they pointed the receiver. Not realizing it was the Big Bang's leftover heat, they thought it was a problem with the antenna and tried to calibrate this noise away. When that didn't work, they went into the antenna and discovered nests of pigeons living in there. They cleaned the nests and droppings of the pigeons out of there, and yet the signal remained. At the same time, a Princeton University team, led by Robert Dicke in America, was trying to find evidence of the cosmic microwave background. When they heard about the Bell Labs result, they immediately realized that the cosmic microwave background had been found. The two scientists had found a cosmic fog that is there in the universe in every direction. The result was a pair of papers in the Astrophysical, one by Penzias and Wilson detailing the observations, and one by Dicke and Co. giving the cosmological interpretation. Penzias and Wilson shared the 1978 Nobel Prize in Physics for their discovery. The cosmic microwave background is a signature of the Big Bang that formed just after the universe began 13.8 billion years ago. Over the intervening billions of years, the universe has expanded and cooled greatly. Due to the expansion of space, the wavelengths of the photons have grown, they have been red-shifted to roughly 1 millimeter, and thus their effective temperature has decreased to just 2.7 Kelvin, or around -270 degrees centigrade, just above absolute zero. These photons fill the universe today. There are roughly 400 in every cubic centimeter of space and create a background glow that shines primarily in the microwave portion of the electromagnetic spectrum, detected by far-infrared and radio telescopes, and is invisible to the naked eye. However, it fills the universe and can be detected everywhere we look. In fact, if we could see microwaves, the entire sky would glow with a brightness that was astonishingly uniform in every direction. The temperature is uniform to better than 1 part in 1,000. This uniformity is one compelling reason to interpret the radiation as remnant heat from the Big Bang. It would be very difficult to imagine a local source of radiation that was this uniform. In fact, many scientists have tried to devise alternative explanations for the source of this radiation, but none have succeeded. A small percentage of the static you see on dead TV stations is leftover radiation from the Big Bang. You're seeing residual effects of the universe's creation. Since light travels at a finite speed, astronomers observing distant objects are looking into the past. Most of the stars that are visible to the naked eye in the night sky are 10 to 100 light years away. Thus, we see them as they were 10 to 100 years ago. We observe Andromeda, the nearest big galaxy, as it was about 2.5 million years ago. Astronomers observing distant galaxies with the Hubble Space Telescope can't see them as they were only a few billion years after the Big Bang. The cosmic microwave background is the furthest back in time we can explore using light. It formed about 380,000 years after the Big Bang, and imprinted on it are traces of the seeds from which the stars and galaxies we can see today eventually formed. The behavior of cosmic microwave background photons moving through the early universe is analogous to the propagation of light through the Earth's atmosphere. Water droplets in a cloud are very effective at scattering light, while light moves freely through clear air. On a cloudy day we can look through the air out towards the clouds, but cannot see through the clouds. Cosmologists studying the cosmic microwave background radiation can look through much of the universe back to when it was opaque. A view back to 380,000 years after the Big Bang. This wall of light is called the surface of last scattering, since it was the last time most of the cosmic microwave background photons directly scattered off of matter. When we make maps of the temperature of the cosmic microwave background, we are mapping this surface of last scattering. There are very small fluctuations imprinted on the cosmic microwave background radiation pattern. These reflect slightly higher and lower densities in the earliest universe. These fluctuations originated immediately after the Big Bang and would later grow under the effect of gravity, giving rise to the large-scale structure like clusters and superclusters of galaxies that we see around us today. Hidden in the pattern of the radiation is a complex story that helps scientists to understand the history of the universe, both before and after the cosmic microwave background was released. Hence there is great interest in studying cosmic microwave background. The light photons wandered through the early universe, just as optical light wanders through a dense fog. According to the Big Bang theory, due to the process of multiple scattering, the frequency spectrum of the cosmic microwave background should have blackbody form. This was indeed measured with tremendous accuracy by the FIRAS experiment on NASA's COBE satellite launched in 1989. Among its key discoveries were that averaged across the whole sky, the cosmic microwave background shows a spectrum that conforms extremely precisely to a so-called black body or pure thermal radiation at a temperature of 2.73 Kelvin, but that it also shows very small temperature fluctuations on the order of 1 part in 100,000 across the sky. These findings were rewarded with the award of the 2006 Nobel Prize in Physics to John Mather and George Smoot. There is no alternative theory yet proposed that predicts this energy spectrum. The accurate measurement of its shape was another important test of the Big Bang theory. NASA's second-generation space mission, the Wilkinson Microwave Anisotropy Probe, was launched in 2001 to study the very small fluctuations in cosmic microwave background in much more detail. Finally, European Space Agency's Planck satellite was launched in 2009 to study the cosmic microwave background in even greater detail than ever before. It covers a wider frequency range and more bands, and at higher sensitivity than Wilkinson Microwave Anisotropy Probe, making it possible to make a much more accurate separation of all of the components of the submillimeter and microwave wavelength sky, including many foreground sources, such as the emission from our own Milky Way galaxy. This thorough picture thus reveals the cosmic microwave background and its tiny fluctuations in much greater detail and precision than previously achieved. Planck's instrument detectors are so sensitive that temperature variations of a few millionths of a degree are distinguishable, providing greater insight to the nature of the density fluctuations present soon after the birth of the universe. Planck's observations, first released in 2013, mapped this cosmic microwave background in unprecedented detail. The cosmic microwave background is remarkably uniform over the entire sky, but tiny variations reveal the imprints of sound waves triggered by quantum fluctuations in the universe just moments after it was born. These imprints, appearing as orange or blue in the Planck map, are the seeds from which matter grew, forming stars, then galaxies, and then clusters of galaxies. The maps give rise to new mysteries. The Big Bang theory says that the cosmic microwave background would be mostly the same, no matter where you look, but southern hemisphere appears slightly redder, warmer than the northern hemisphere. Also, question arises: if space appeared after Big Bang, then what the universe is expanding into. Like if universe started with a single point, then there must be an end, an edge which should be the farthest point till which universe has expanded. What lies beyond that? For example, if we consider a balloon as universe and air inside it as space. If we inflate the balloon in water, then the balloon is expanding into water and air inside it is expanding. What lies beyond balloon is water. Similarly, there must be something in which universe is expanding into. Other big question is what gave rise to Big Bang. Scientists are yet to explain this. Although there are models that speculate about these questions, none of them have made realistically testable predictions as of yet. However, recently there has been ever more evidence that suggests most of the ingredients making up the universe come in forms that we cannot see. Researchers think most of the cosmos is made up of matter and energy that cannot be sensed with conventional instruments, leading to the names dark matter and dark energy.